Welcome to the Unit 5 project, which is where you're going to take your barn quilt, and if you didn't do a barn quilt, then you get to make a barn quilt before you can do this project. And in your barn quilt, you were supposed to identify two triangles and label one ABC and the other DEF. In this project, you are going to prove that triangle ABC is congruent to triangle DEF. Now you've got two options to do this. You can use, actually three, you can use hypotenuse leg if your triangle's a right triangle. You can use side, 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 or you can use side, angle, side. It is up to you. So I will demonstrate this project, and I am going to choose, I do not have a right triangle, so I'm going to choose side, side, side. But be aware that you're welcome to do hypotenuse leg, and you're welcome to do side, angle, side. So just because I'm doing side, side, side doesn't mean that you need to do that also. So the first thing we're going to have to do is we're going to have to find the lengths of our sides. And we're going to do this using the distance formula. Now, if your triangles by chance touch, and there's a side that is congruent by the reflexive property, then you'll have less work than what I'm going to need to do. If you have a right triangle, then you can use hypotenuse leg, and you could do less work also. So I'm going to start with finding the coordinates of my vertices. This is my origin, this is my x-axis, this is my y-axis, and here's my origin. So point C is going to be, I've gone over none and up 2. To reach B, I have moved left 2 and up 1, 2, 3, 4, 5, 6. So I've gone left 2, up 6. And then for A, I've moved 1, 2, 3, negative 3, up 2. So that's negative 3, 2. All right, so as you find these lengths, then you would need to use correct notation so that I can follow what you're doing. For example, if I want the length of segment AB, then I'm going to write segment AB equals, and then I'll show the work. So AB is going to be negative 2 minus negative 3 quantity squared plus 2 minus 6 squared, which is going to be, that's going to be 2 plus negative 3, which is going to be 1 squared plus negative 4 squared, which is going to be the square root of 1 plus 16, which is the square root of 17. All right, so now I'm going to do BC, and BC is going to be the square root of negative 2 minus 0 squared plus 6 minus 2 squared, which gives me negative 2 squared plus 4 squared, or the square root of 4 plus 16, which is equal to the square root of 20. And that is going to be the square root of 4 times 5, which is 2 square root of 5. So I want your radicals in simplest radical form. And then we've got AC. Now AC is horizontal. And because AC is horizontal, I can use the distance between 2 points that we learned in Unit 1, where I take, this is a y value or an x value of 0, subtract negative 3 for 3 units. Now certainly if you use the distance formula, it would also work. Alright, so now I'm going to need my next triangle down here. So D happens to be over 0 down 2. E, I have moved over a positive 3 down 2, so that should be a negative 2. And F, I've moved over 1, 2, down 1, 2, 3, 4, 5, 6. So this is going to be a positive 2, negative 6. So I need to find the length of these 3 segments also. So I'm going to label, I will start with DE, EF. EF is equal to the square root of 2 subtract 3 squared plus negative 6 subtract negative 2 squared. It's going to be plus positive 2. So that's going to give me negative 1 squared plus negative 4 squared is the square root of 1 plus 16, which is the square root of 17. So now we've got EF. I said BC, so I'm going to say FD. FD is equal to the square root of FD. So let's say 2 minus 0 squared plus negative 6 minus a minus 2 squared, and that would be plus positive. So that's going to be 2 squared minus a negative 4 squared, which is going to be 4 plus 16, which is square root of 20, which is 2 square root of 5. And again, that's a horizontal segment, so ED is going to equal, this is a unit of 3, minus 0 for 3. Again, we can use the quadratic formula on that. All right, so if I'm following the rubric, I have found the lengths of the sides. Part 2, angle measures are not appropriate for what I'm doing here. So I'm going to go to a new page, and I'm going to begin my proof. We always begin the proof with given. So what have I been given? I have been given that AB is square root of 17. I have been given that BC is 2 square root of 5, and I've been given that AC is equal to 3. I've also been given that EF is square root of 17. I've been given that FD is 2 square root of 5, and I've been given that ED is 3. Now, I need to prove either, well, I'm not going to prove any segments because I already have my segments. So I think I'm going to prove that angle BAC, that angle BAC is congruent. Now when you do this, make sure that you correspond your vertices well. BAC is going to be FED. Is congruent to angle FED. So this is my statement column. This is my reason column. So the first thing I think I'm going to say is that AB is equal to the square root of 17. We know BC is equal to 2 square root of 5. We know AC is equal to 3. We know EF is square root of 17. We know FD is 2 square root of 5. And we know ED is 3. How do I know this? There should be 1, because it is given. So from here, I'm going to make the statement that AB, segment AB, is congruent to segment EF. How do I know that? By definition of congruent segments. Definition of congruent segments are segments with equal length. And then 3, I'm going to say that BC is congruent to segment FD, and that's going to be definition of congruent segments. Then I will say that AC segment is congruent to segment ED, and that again is by definition of congruent segments. Now, if you had a reflexive, then you would have a reflexive in here. So this allows me to state that triangle ABC is congruent to triangle, alright, we've got ABC, so EFD. EFD. Why? Minus side, side, side. So last but not least, I know that triangle BAC is congruent to angle FED, and that's going to be by corresponding parts. Congruent triangles are congruent. Alright, so just let me make some statements in case you did side angle side. If you measure an angle, then you would say something like measure of angle M and O was equal to 45 degrees. Measure, and we should say measure of angle PQR is equal to 45 degrees. And then that would be in your given, and then this part would be in your proof, stating that these two angles are congruent, because definition of congruent angles with the same measure. If you're doing hypotenuse leg requires right triangles. So if you have hypotenuse legs, then you should have perpendicular segments. So you're going to have to find the slope of those perpendicular segments. Perhaps one slope is 0, perhaps another slope is undefined. That would mean horizontal and vertical. So you would say, let's say, segment HL is perpendicular to segment KO because the slopes are opposite reciprocals. Now, a fancy way of saying because the slopes are opposite reciprocals is to say the product of the slopes is -1. Now, if you were to multiply those two slopes, you would get -1. So then you'd have to identify an angle. Let's say it's angle HLP and angle KOM are right angles. And that would be definition of perpendicular lines. And then from there, we would say triangle HLP and triangle KOM are right triangles. And that would be definition of right triangles. So if you want to use HL, you've got to establish that the triangles are congruent. And if your slopes come out to be 0 and undefined, it's because the slopes were opposite reciprocals. And you should see that one might be 0 over 3, the other one might be -3 over 0. But you should be able to see that. All right, so that's your first proof. So then the second proof is going to be more of a paragraph proof, and that is going to be using isometries. So I'm going to, I think, work on my second proof here so that I can see what I'm doing, since I can't see both of them at the same time. Maybe I could. Let me see if I can do a split screen. There we go. All right. So I'm going to, there we go. So now I can see both. All right. So I am thinking that if I were to translate this triangle to the right, maybe what I'll do is reflect my triangle. I could do a double reflection. I could probably do a rotation. So there's more than one way I could do this. So I think I'm going to do a double reflection. I could do a rotation. All right, so how am I going to go about this? All right, so I think I'll say perform. And what I'm going to do is I'm going to reflect. So that's a large R. Perform the reflection. And this is going to be about the y-axis, which is x equals 0, of triangle ABC to give me A prime, and I should have a triangle here. That will give me triangle A prime, B prime, C prime. So what I've done is I have reflected the green, and I now have, it is now, I have now put it here. That's where I am now. So now what I want to do is I want to reflect. I'm using my cursor. Right, I want to reflect this triangle over the x-axis to get to that one. So I think now I'm going to say perform a reflection about y equals 0. Now I'm reflecting triangle A prime, B prime, C prime, and it's going to give me triangle, so I did A, B, C, so it's going to give me E, F, D. Alright, so now I can say that triangle A, B, C is congruent to triangle E, F, D, because two reflections map triangle ABC onto triangle EFD. Mapping onto kind of tells you that it makes that triangle fall on top of that one in a sophisticated way. Since reflections are isometries, which preserve distance and angle measured, the triangles are congruent. Alright, then I can say that angle BAC is congruent to FED because corresponding parts of congruent triangles are congruent. So this is the isometry piece. So what I'm highlighting in yellow. Alright, I could have rotated, I could have used a rotation about the origin of 180 degrees of triangle ABC, and that would fall then on, A would map all the way over to D, onto, actually map to E, onto triangle EFD. So I could have replaced these two things with this one and then gone through the rest of the proof. So it all depends on how your things are oriented. You might have to slide, then flip. You might have to do several flips. You might have to rotate. You might have to do a glide reflection. But anyway, this is the way that the second one is done. So capital R for reflection, little r for rotation, and if you remember, if you have to translate, then we do like 3, 2, which means you move 3 units to the right and then 2 units up. So that is how you do the second one. So this is your Unit 5 project.